In the California gold rush of 1849, it was merchants, not prospectors, that were truly successful. Individuals like Levi Strauss sold durable clothes and Sam Brannan made shovels and pickaxes. This led to the maxim, in a gold rush, build tools. Well, an equivalent gold rush is going on today, the rush for cellular stem cell therapeutics, and our quest to build effective tools. Now, stem cell therapeutics hold great promise for replacing and healing tissues that were previously untreatable. Things like heart, kidney, spinal tissues, lung, and even the hope of regenerating joints from degenerative joint diseases. But unfortunately, in the United States, the only FDA-approved stem cell therapeutics are for immune and blood disorders. This incredible gap between opportunity and reality lies with the many challenges still plaguing stem cell therapeutics. My work in the College of Education and Human Development centers around the use of reactive inorganic biomaterials for soft tissue regeneration. Now, because this may not sound particularly exciting to many of you, let's look at this in the context of something we can likely all get excited about: prime rib. In the same way that a well-marbled prime rib can be cooked to perfection over 6 to 7 hours, but completely destroyed at high heat in 30 minutes or less, my materials, when reacted in a body system over several days, form a very porous surface crust that is highly adherent to cells. They like to stick to it. While I was investigating this, I began forming a collaboration with Dr. Peter Neem in veterinary integrative biosciences. And he's studied stem cell therapeutics for quite a while. And one of the problems he and others see, is that these cells, when they're injected in a living system, they like to stick together, form pockets that are too great for oxygen to diffuse to the center of, and many of them die and fail to diffuse freely and do what they're supposed to do. Now, a classic approach to trying to prevent this is to place these cells within a thick solution or upon a gel so that it'll keep the cells apart. But this also has some challenges in that they still may not fully diffuse in the distance they're supposed to. And so, one of the things that we were interested in knowing is, what if, instead of placing cells within or upon a material, we placed a material upon the cells? So we asked two questions. If we take our materials, place them in a bioreactor and react them, and then isolate them back out, will they combine with stem cells? And then two, when these materials have been bound with stem cells, if we inject it in, will it keep them from sticking together and allow them to disperse? So we did this. We had some mouse muscle that we injected with stem cells, and then we combined our material that we call Ageria with the stem cells and injected them in, and we found that it worked. Stem cells injected alone formed a pocket that was too great for oxygen to diffuse, and when combined with our materials, they dispersed, limiting pocket size. And so we called this the cellular chaperone system. We went on then in multiple organisms, one even funded by the Advancing Discovery to Market Award from Texas A&M, to look at the effectiveness of this material. And a provisional patent was filed last year, and a company, Scrum Bio, licensed the technology prior to it being presented on an international stage in Italy. And I'm excited to report that just this month, a full patent was filed by Texas A&M. Now, we're currently in the process of making manufacturing partnerships and partners with individuals whose resources and reach far exceed our own to try to maximize its full potential. Now, we don't know when this stem cell gold rush will end, but we would certainly like to play a role in developing some of its most impactful tools before it does. Thank you.